Okay, so this is the lab report for Physics 22 Lab 2, where we're going to revisit Lab 1, which was charge tape. In this lab, we're going to look back at the previous charge tape lab by more accurately analyzing the real-world physics of charge by looking at things as a dispersed charge rather than a point charge. To do this, we're going to create a more advanced computer model in GlowScript to calculate electric force compared to what we did last time. The results that we found in the lab is the charge tape is going to be 2.5 times 10 to the 8 newtons of the force. The electric field is going to be 2.118 times 10 to the negative 3 newtons, and the magnitude of the force of gravity is going to be 2.18 times 10 to the negative 3 newtons as well. There's some key principles that we need to understand for this lab are Newton's second law, which is force equals mass times acceleration. We're also going to need Newton's third law, which is Newton's second law, that every force has an equal and opposite reaction. And we are also going to need Coulomb's law, which you can see written out as force equals Q1 times Q2 over 4 pi epsilon naught times divided by r squared. We also need to understand that like charges repel and objects that are oppositely charged attract. In the original lab, we found the charge, or we created a charge on the tape by sticking a tape on top of another and then quickly unsticking them, which creates a charge. We're going to need to determine the charge of these objects by bringing them close to one another and figuring out what sort of charge they are relative to what we known a known charge, the test of the force of these by bringing them together, and you can see that they repel. We can also see that they are positive as a result, and we'll use this data to calculate the charge in the lab. We've got a few key assumptions that we're going to assume that there's no air resistance. Additionally, the charges are equal even though they're unlikely to be perfectly equal. We also know that we're going to have some source of error because some data is found via an approximation and rounding, but we're also going to have outside systems affecting the charge because the charge will not be perfectly stationary. It will be constantly changing, and there's also going to be human error involved in the system here. That is going to be the top UT tape in the surroundings and the other tape and the objects in the room that have a charge that are going to affect these initial conditions. And we're going to assume that they will start with a neutral charge even though they likely don't. We're also going to assume that they're equal size here. You can see the code now where we find the force on the top UT tape and the force on the bottom tape. We now know U, and then here you can use the data found here to help create the vectors that are simulated on the actual computer model. The prediction will be that the tape will be repelled by the other, causing it to float, and the observation was that it was indeed caused to float when the tapes were approximately 0.005 meters away from each other. We see that both models showed the tape to float when the other came nearby, but the difference is that they needed to be closer in the model, and we also need U, the resulting force is a lot weaker than anticipated. So some what-if questions is, what if the model had the charges of a single point charge? The tape would have a lesser charge and resulting force due to electricity. Due to the electric field, the magnitude was lesser than the magnitude of the charge we assume to be a point charge because the charge is spread out over a large area instead of just being a single point. And why do these differ? This is because, like I said, point charges are simulated. There's nothing around them, and a line charge is spread out over an area, which would cause this to be more realistic of the two charges, because in real life, point charges aren't necessarily a thing, and the line charge would be more closer to what you expect and actually see. Thank you.